Today I want to show how you can use markers to measure stuff by using sensors, and also I want to show some post-processing. We have a simple robot, as you can see, and we want to plot some graphs and do some post-processing and use markers to measure the size of the pipe and the location of the robot. A marker is basically a coordinate system which you can define on an object. You can also use smart points. The only difference is that the smart point can be defined anywhere. Doesn't need to be on an object. Here I want to represent the pipe by using markers, so I'm gonna put markers every 90 degrees around the body of the pipe. The angle on arc seems to be the best option here, but of course you can use any other options or methods to fit some points around the pipe. Now we have the sensors and we can run the simulation and then plots the results. You can use XY result view here to plot almost anything. So you just need to click on whatever you want to plot or view the result on Motion Navigator. Then you can move the XY view and plot like this. Now you can customize this plot. For example, we can change the x-axis limits or units from here. Now we have both distances from the sides, and if I check the difference between these two, I can see if the robot is on the center. To do that, we can use curve operation. Here you see that I have the available curves. If I select both and add them together, since one of them is negative, I will get the difference between them. Now we can see that it is around 0 for this straight pipe, and starts to increase as it turns. I can limit it to the time span that I need, and here we can see it goes to the maximum 152 millimeters. Now I can also plot the torque on the joints. So if you move down to the forces, you see the torque magnitude for that specific joint. We have a spike in the beginning, which we can of course remove it by limiting the time axis, and you see this kind of torque on the wheel. It's a bit noisy for some reasons, mainly because the speed is too high, the rotation speed, and also the parameters of the contact. You can also check separately for each axis. Now let's go back to this negative number from the markers. Basically, the software is measuring from the positive side of the first marker to the next one. So what we should do is to flip the x-axis so the markers are toward each other along the x-axis. Now we did the simulation again, and as you can see, number is now positive. So I can plot the other one as well, and by adding up these two, I get the distance between the two markers, or basically the outer diameter of the pipe. Here I still have the old expressions, so I need to reset the formulas before I add them together. As you can see, we get around 200 millimeters, 220 actually, as the size of the pipe. Now let's see how we can fix the torque. the torque is really noisy because of the contact, because it is actually slipping a lot. If you look again, let me limit the time. Here you see that the torque is very noisy, and if we average it like this, we probably don't get a good number. The problem is the stiffness and other parameters like damping in the contact. Now here, if you click on the question mark to get to the documentation, there is a nice guideline for contact materials. Here you will find most of the materials that we are using here. So we have acrylic and dry rubber. We have a contact between these two, so I'm going down to the list and find the contact between 22 and 20, and these are the parameters that we're going to use here, which are recommended by NX. Also, you need to make sure that your units are correct when you input these numbers. And this last one is only for Adams solver, so we are not going to use this one. So this one is okay. I can now copy this contact parameters and paste it into other contacts. Now we can run the simulation again. Okay. Now let's see the result. Since the stiffness is lower than before, this material stiffness for the contact, we have a little bit of we have basically lower noise, but as you can see, it is still very noisy. So we probably need more damping on the contacts, but the best practice is actually to reduce the speed of rotation so we don't get that much slipping. So here we can use some plot functions to see, for example, linear average or the RMS of this plot. Here, for example, is the linear average for that range, or the RMS.